Welcome to another Starin AV Meetup coffee break, everyone. AV Meetup comes from our local in-person events where we've taken folks from San Francisco to Boston, Chicago, Philadelphia, and several other markets out on boat trips in some cases, and we've shown some working systems in the process. So the AV Meetup on the web has two versions. The coffee break, where under the time it takes to sip a cup of joe, we're going to cover an application. We cover application-driven topics. And the second version is a workshop that goes deep into the subject for over the course of an hour. Today, you're in a workshop. Note during the presentation we've muted the mics just to keep the noise floor down. It doesn't mean we don't want to hear from you. So for questions, please use the chat window. Some of you have already found the chat window, and we'll be sure to address your questions at the end. Also, be sure to stay with us to get your super cool AV over IP t-shirt. Yes, you're part of the beginning of our series on network solutions, and your responsibility is to show the world that you know AV over IP with your cool t-shirt. So make sure that we have your size if you haven't given it to us in the registration process. So I want to introduce our presenter today, Phil Hippensteel. He's a professor, researcher, writer, and consultant that's worked in both the AV and the IT industries. As a teacher, he spent over 40 years in higher education and finished his full-time career at Penn State, where he currently teaches part-time. This is the part that amazes me. Over 3 decades, he has taught nearly 12,000 students across 27 states. He's an active researcher working on IP video transport and network performance. For 4 years, he wrote a column called Ask Professor Phil for AV Technology magazine, and his column has just been modified to be a tutorial series called Professor Phil's Bite-Sized Lessons. He has also written dozens of feature articles for AV Technology, Information Week, and Network World magazines. So, without further delay, Dr. Phil, take it away.
Thanks, Neil. I'm happy to be here, and I want to thank Starin for conducting these workshops. It is true that I've spent most of my life teaching IP-related topics. I actually started out as a mathematician and morphed over into the computer area and ended up teaching communications because nobody on my staff would learn about networks. And I've spent the last 30 years involved in teaching and writing and researching about networks. So we'll get started. We've got a kind of heavy schedule here today, and we've got a lot to cover. I tried to pick topics for this session which I found over my couple of decades of teaching this that people have the most trouble with. So we're going to start with something that's a little challenging, but probably the thing that will be most useful to you to take forward into the future. We need to understand the subnet mask, and over the years I've learned that when you try to teach the subnet mask and people don't understand binary, they have a great deal of difficulty with the topic. So I kind of drag people through a quick review of binary. When we get to the point that we try some tricks to create subnet masks in order to assign addresses, we understand what we're doing. We'll also spend some time with the idea of the IP address itself. We're going to focus only on IP version 4. In the AV marketplace, there's very little IP version 6 out there yet, so what we learn about IP version 4 would probably do us for the next decade or so, and we'll cover some basics about that. In a later presentation, we'll go into a little more detail, and then we'll spend a considerable amount of time during this hour, probably roughly half an hour, on the idea of the subnet mask and how you pick the subnet mask, how you interpret the subnet mask, and what difference it makes. The subnet mask is extremely important because the subnet mask is what determines the size of the network. And unless all the devices have the same understanding, packets get misrouted. So it's important to have the right address, or rather not only the right addresses on the computers, but it's equally important to have the right subnet mask. The last and probably most important reason to understand the subnet mask is the IT department's going to expect you to understand it. When we're putting devices on networks today that have IP addresses, they're likely going to interconnect or be associated with the corporate network. And the IT department doesn't want to take the time to try to teach us the basic concepts about subnet mask, so we need to understand it for that purpose. Then we'll do quite a few examples where we assign addresses. We'll assign addresses for big networks, small networks, change the subnet mask and see what that does. Then finally we'll introduce the idea of the VLAN. And the primary reason for doing that is because it's fairly commonly, mistakenly thought that a VLAN segment is the same thing as a subnet. It is not. And we need to understand the difference between those two and how the subnet can route packets differently than a VLAN can make packets flow. So let's look at the topic of binary. Binary representation is based on 2 digits, 0 and 1. Our ordinary number system is based on 10 digits, 0 through 9. When we run out of digits to represent a bigger number like 10, we assume that we put 1 in the next column and 0 to show the number of units. So we say one group of 10 and no units. Then we'd say one group of 10 and 1 unit, one group of 10 and 2 units, and so forth. That's how we count. In binary, we do the same thing, but we only have 2 digits. So we have 0. If we increase, we go to 1. If we increase, we go to one group of 2 and no units, one group of 2 and 1 unit, and then 2 groups of 2 or 4 and no units, 4 and 1 unit, 4 and 2, that is 4, a group of 2 and no units, and so forth. One of the important things to understand here is that when we added a digit to give us 2 digits here, we doubled the number of things we can represent. With 2 digits, we could only represent 0 and 1. But with 2 digits, we can represent 4 things. When we introduce the next digit, and we have 3 digits, we can represent 8 things, 0 through 7. So adding a 1 to the binary expression allows us to represent twice as many things. Now within a single byte, which is 8 bits long, within a byte, we have 8-bit positions. And if you add up the value of this, a unit plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128, it adds up to decimal 255. So in a single byte, the highest number we can represent is 255. With 1 byte, we can represent all the values from 0 through 255. That idea, combined with the idea that when we add a bit into the binary representation, it doubles the number of things we can represent, gives us the 2 basic concepts we need to understand addresses and masks. If we compare the decimal representation to the binary representation, the decimal representation 327 is nothing more than a shorthand for 3 times 10 groups of 10, 3 times 100, plus 2 times 10, plus 7. If we write this number 1101, it means 18 plus 14 plus 02s plus 1, decimal 13. So if we look at the binary within an IP address, often it's important to look at the binary that's in the last byte or the last 2 bytes. If we take the number 69 and we represent the powers of 2, or the 2s, 4s, 8s, 16s, 32s, 64s, and 128, we have 0 128s plus 64 plus 0 32s plus 0 16s plus 0 8s plus 1 4 plus 0 2s and 1, and that adds up to 69. And as a result, it can be represented this way, as a result, decimal 69 is the same thing as the binary byte 0 1 0 0 0 1 0 1. So take a second or two. If you have a piece of paper, write down this binary number, 1 0 0 1 1. Once again, 1 0 0 1 1. See if you can determine the decimal value of it. Well, it's 16 plus 2 plus 1, or 19. If you got 19, you're getting the idea. Hopefully we have a bunch of 19s out there right now. So let's talk about IP addresses. You'll hear technicians and engineers talk about the class of an address. They'll say, well, we use the Class B address, or we use the Class A address. Class A, B, and C addresses are nothing more than a convenient way to talk about the addresses. It's not a system that's actually used within devices. But for convenience sake, we can say that an address is a Class A address if the first byte in the address, in this case this byte here, is between 1 and 126. This is 10. That falls in that range. So this is considered a Class A address. If the first byte falls between 128 and 191, then this is Class B address. And by the way, by convention, if the mask doesn't change this, the fact that it's a Class B address means that the first 2 bytes designate the network. So we would say that this is a Class B address, and the network is defined by these 2 bytes here, 137.15. Class C addresses, like the ones that you typically use in your home router, begin with some number between 192 and 223. and 192 makes it a Class C address. And the convention there is, unless the mask changes it, the first 3 bytes define the network portion. Class D addresses are multicast addresses sent to a group of devices, and they start with a number between 224 and 239. For example, the address 224.0.7 is a multicast address. Multicasting is something you probably won't run into unless you get involved in IPTV and MPEG transport networks. They're especially used by carriers like Comcast and Verizon, but typically they're not used in most AV networks quite yet. They're growing in importance and probably will begin to play a bigger role as time goes on. So that's the system called the class address system. And again, it's for convenience of discussion. It serves no other purpose than to allow us to basically have a framework to talk about larger networks and smaller networks. Another very important concept is the difference between private and public addresses, or private and global addresses. Private addresses can be used inside companies. They don't have to be registered with anybody, so you can use them any way you want, but you cannot send private addresses out on the internet. Public addresses are addresses that are registered with the Internet Number Assigning Authority, and they're assigned to companies after they're registered, and they may be used on the internet. But we reserve certain ranges of IP addresses for private use. Anything starting with a 10 is a private address. Anything starting with a 192.168 is a private address. Now this is a lesser used private address range, 172.176.16 through 172.31.255.55, in other words up to, but not including 172.32. That range is also reserved for private use, but they've begun to give some of those out. So most advisors tell us it's a good idea to stay away from using these addresses unless you're real comfortable with this system. Better to stick to these guys when you have a big network, these guys when you have a small network. Finally, the last reservation that's important is the address starting with 127.anything is reserved for my own computer. So I can type a command, for example, like ping 127.0.0.1 or ping 127.12.22.38 if it makes me happy. And basically it will send it to my own computer. Basically the software, my protocol stack will send the ping to my network interface card and see if I get a reply back. It's a way to test whether or not your own TCP/IP stack is actually working. So let's turn to the mask. The purpose of the mask is to let everybody in one particular network know how we're breaking down the IP address into 2 parts. We're segmenting the address into a network portion and a computer portion. And the mask is telling us how to do that. So for example, if we have an address like 192.168.15.3 and the people who set the network up pick this mask, which is 24 ones followed by 8 zeros, they've decided that they want these 24 ones to tell us that 24 bits in this address belong to the network designation. So the boundary that we're referring to here, the boundary is here. This defines the network. This defines the computer on the network. So we would say that the network is 192.168.15 and use the lowest possible value for this position, 0, and say the network is 192.168.15.0. We'd never enter the mask into the computer this way. This is the way the computer or the router would use the mask. But the way we enter it into the screen when we tell what the mask is to put it in a decimal. So we put in 255.255.255.0. Then combining this address and this mask, we can use this shorthand notation and say the computer has the address 192.168.15.3 with a /24-bit mask. We call it a 24-bit mask, meaning it has 24 ones in it, followed by 8 zeros. So again, where the ones are in the mask, where the binary ones are in the mask, defines the network portion. Where the binary zeros are in the mask defines the computer designation. Any of you who know anything about programming in real low-level languages like assembler know that it's very easy for a computer to compare this in binary to this in binary and see that the separation is right here. It makes it real easy for the computer to process. Here's an example with a class B address. See the 143? The class B address is 143.157.13.191, and they've chosen a mask of 255, 8 ones, 255, 8 ones, 0, 8 zeros, 0, 8 zeros, 255, 255, 0, 0. That's the mask we would enter in the software. The shorthand notation would be 143.157.13.191 with a slash to say 16 ones are in the mask, a 16-bit mask. And this tells us that the network is 143.157.00 because the 16 bits tell us that these 2 bytes here designate the network. And so we use the lowest possible value at this end to make the network address 143.157.0.0. Here's another example. In this example, we have a class A address, and by convention, if it worked out nicely and we didn't need to subdivide the network any further, we could say the network was 10.0.0.0, and this computer is 13.131.52 on that network 10. So we use a mask that has 8 ones in it, followed by 24 zeros. The 8 ones tell us first byte designates the network. The bits back here can be used to designate computers. So this particular computer, 13.131.52 on network 10, using an 8-bit mask, is only one of a huge number of computers that could be on here. You could actually assign computers here, starting with 0.0.1 the whole way up through 255.255.254. You can't put all 255s here. We'll talk about that in just a minute. But this could be a very large network. Class A networks can be extremely large. Class networks are generally much, much smaller. Class C networks are much, much smaller. Now this is where it gets tricky in exercise in example 4. In this case, somebody decided to use what would sometimes be called a non-conventional mask. They decided to use a 17-bit mask on a class B address. So it's 143.157.152.167. 8 ones, followed by 8 ones, followed by a single 1, and then 15 zeros. So what we're doing here is designating a network with this byte, and 1 bit out of this byte. See where the binary comes in? We're using all 8 bits here, 8 bits here, but only 1 bit here. And when we write this mask in decimal notation, we write 255.255.128. If you look at that byte, everything's 0 except that position, which has a value of 128. So it's 255, 128, 0 is a mask. We write this as a shorthand notation, 143, 157, 152, 67, /17 to correspond to the 17 ones. And we say the computer is on, be careful, 143.157.128.0. This is a network, and it's not a Class C network. We'll come back to this again to figure out why it's 128. In this example here, we take what would normally be a Class C address, 192.168.3.77, but this time we put 26 ones in the mask, 192.168.3.77/26. And in this case, because we have 26 ones here, the network is 192.168.3.64, because the first 2 bits here are now being used to designate the network. The first 2 bits are being used to designate the network. And in binary, the first 2 bits of this number are 0, 1. And so this position here gives us the 64 that we see here. I'm going to do another example after we assign some addresses, and we have a little bit of a shortcut that probably will help clarify how this works. So, after we've looked at the mask and we've looked at IP addresses, an obvious question is, well, what are the rules for using IP addresses in subnet masks? And here are basically the 5 critical rules. The network address is the lowest possible address in the range that's created by using a particular mask. The network address is the lowest possible address in that range. We reserve the highest address in that range to send broadcasts within the subnet. That's why in one case I mentioned that you couldn't use 255. It was the highest value. This is the most important rule of all. Things go crazy if you don't follow this rule. All devices within a subnetwork have to use the same mask. It's the subnet mask which is determining the size of the network, and for packets to be properly routed by the devices and the routers, everyone has to have the same understanding about the size of the network. That's determined by the mask. So all devices within the subnetwork have to use the same mask. And like end stations, router interfaces have to be treated as if they are an end station. They have to have an IP address. So subnets are normally bounded by end stations, router interfaces, or firewalls, because basically a firewall is playing the role of a router. So let's assign addresses in a fairly simple situation, and then we'll assign addresses in a little more complicated situation. In this case, we have 4 networks, 4 subnetworks. This network here is bounded by this computer, this camera, and this router interface. So this is one physical network. This is an Ethernet switch that's in here, what we call a layer 2 switch. By the way, the layer 2 switch may have an address in it, but that's an address that's only used for one purpose, and that's to address the software that's in the switch. So for the purposes of relaying packets, the address that would be in the switch plays no role at all. That's important to understand. So we have a network here, which we're just going to designate as 10010 because we want to use this position here. We want to use that 1, the 3rd byte, to indicate the difference between the networks. So we'll make this network 1001. We'll make this network 1002, bounded by these 3 interfaces here. This 1003, and this 1004. Within 1001, 0, with a 24-bit mask, we can put .8, 1001.8, as the computer's address here, make the camera 1001.7, and typically, not by any rule, but typically the lowest possible value that you can assign is given to the router interface. So the chances are you can almost guess that this is going to be 10.0.1.1. Then this is .8, this is .7, there might be a .3, .5, .22, .51, and so forth. This network here, 1002, has no devices, but these are interfaces. So they would probably get addresses 2.1, 2.2, 2.3. Likewise here, we'd probably put 3.1 here, 3.2 here, 3. Here, and make the camera something higher, 3.7. And finally, if we had 2 interfaces here that these servers connect to, then we'd probably put 4.1 on one interface and 4.2 on the other interface, and then make the end devices here a higher number like 4.225 or 4.224. I picked these addresses here because it's not that unconventional, it's fairly common, to use high values for the servers. Some people like to use the lowest possible value on the router interfaces and use much higher values on things like servers and firewalls. Within this network then, we've got 3.7 that's the only end device that's connected. Here we have 2 end devices, and they're connected into what would probably be a single interface with a switch sitting in this position here. But this is where it gets fun. Now, IT department says, sure, you can put your cameras on your network, but you have to use the address 192.168.1.0. Well, at home, 192.168.1.0 only gives us one network. What we have to figure out is, how do we handle that situation when we have 4 networks, 1, 2, 3, and 4? The answer is we're going to have to use a clever mask. We're going to have to change the mask that normally would be used, say in a home router situation. We're going to change that mask from 255, 255, 255, 0 and use a 26-bit mask. That will take the range of addresses normally allowed by 192.168.1.0. It'll take that range of addresses, cut it in half, and cut it in half again, and give us 4 partitions. We'll have a network 192.168.1.0, one that's 192.168.1.64, one that's 192.168.1.128, and one that's 192.168.192. 4 separate networks, all carved out of the range that normally we would have here when we have one network. So the little shortcut looks something like this. If this is the network assignment we've been given and we use a 24-bit mask, we'll get one network. But if we add a bit, 1 bit into the mask and make it 25 bits, we'll double the number of things we can represent. We'll double the number of networks. We'll take this range that normally would go from 0 to 255 and we'll break it in half. And we'll have a range that goes from 0 up through 127 and a range that goes from 128 through 255. So we'll get 2 separate networks. We needed 4, so we'll add another bit. That will break these in half again, and we'll get 4 ranges. One that starts 1.0, one that starts at 64, one that starts at 128, and one that starts at 192. If we needed to, we could actually add another bit, split these in half, and we'd end up with 8 subnetworks, all carved out of the same address space that normally would give us 1. So increasing a bit, the number of ones in the mask, from 24 to 25, 26 to 27, each time doubles the number of networks we can get. So we're going to use this scheme here with a 26-bit mask. And here's how it works. First, this will be network 192.168.1.0 with a 26-bit mask. And when we do that, we now have this router, assuming it's routing packets into a range of addresses that go from 0 through 63. And we can pick 7 for this computer, and we can pick 9 for this camera. This network here has to be given a designation, so we use the next range, 192.168.1.64, and probably put .65 here, .66 here, and .67 here. We'll put 192.168.1.128 in as the network designation for this network, probably make this 129, 130, 131, and then we can make the camera something like 133, 192.168.1.133.26. Finally, this would be the range that starts with 192.168.1.192, and we can pick values from that 192 up to 255, put 201 on this video recorder, and put 202 on this DNS server. Now, if you're getting the idea of how this works, let's suppose for some reason that the camera here needed to send an IP broadcast to everybody in its own network. It would use the highest address allowed in this range created by this subnet mask. And we said that the range went from 128 to 191. So a broadcast message would be sent from this camera in this network to 192.168.1.191. It's the highest address allowed in the range that's created by this mask. So that's how subnet masks and IP addresses work. You might want to keep that last sheet from the slides around someplace and use it as a cheat sheet until the idea kind of crystallizes in your mind. So let's turn to Ethernet LANs and virtual area network, VLANs. Traditional Ethernet, which was created, by the way, real close to 1980, actually first written down for Xerox in 1978, was standardized first version in 1980, and the follow-on succession of history is almost unbelievable. Anybody who was around then, I remember a telephone company salesman walking into my office and handing me a book about ISDN and said this was the wave of the future. And he said, here's one on this Ethernet stuff. And he said, we don't know much about it or if it's ever going to go anywhere. Well, now it practically owns the world of local area networks here some 35 years later. But in any case, Ethernet is a really simple technology. It's based on a data frame like this, which is between 64 bytes long and 1,518 bytes. There's a 6-byte destination address, 6 bytes, a 6-byte source address. These are what we call the MAC addresses. They're the hardware address that's receiving it, the hardware address of the NIC card that's sending it. Then there's a 2-byte type field. Every data frame has a field like this in it that says what comes next. And this type field has a code that tells us what's in here. For example, this type code would be 0080 if this contained an IP packet. And 95% of the time it does. It would contain 001 if this contained a packet like a ping. This field here, quite frankly, historically, it's interesting to know that this field here ended up maximum 1,500 bytes long because half of the group standardizing it wanted 1,000 and half the group wanted 2,000, and somebody must have said, well, then let's compromise. We'll make it 1,500 bytes long. And the world is now living with the fact that an Ethernet frame field is 1,500 bytes long in conventional Ethernet. Then there's an error check. The sender takes all of this data here, computes a code that's 4 bytes long, sticks it in here, sends this frame out to the destination address, and the receiver reruns the error check to make sure that none of the data was corrupted. So Ethernet, 64 bytes, 1,518 bytes total, is sent from a NIC card to a NIC card. Notice, no routing, no quality of service, nothing like that. Those things had to be added in later. Now, in order to change the way the frame would be relayed on the network by the Ethernet switches, in order to change the conventional way, they came up with the concept of VLANs. And a VLAN tag is inserted in here. After the 6-byte address, 2-byte type field, they put a 4-byte field in here called a VLAN tag. And this contains a code which the switches can use to artificially create what appear to be separate physical networks. This is the way things would flow if you don't have any VLANs or any AVB bridges or any MPLS in order to change things. This would be conventional Ethernet with inexpensive switches. Every switch contains a table in it called a filtering table. The filtering table has addresses of devices like these 3, A, B, and C, and the port to which they can be reached if you sent the packet out that port. So it says device A is off of port 1. Device B can be reached through port 12. Device C can be reached through that same port. So Ethernet frames will be switched through the network according to the active links that are here. It's important to notice that we have some loops possible here, but these are dashed here to indicate that they're inactive. There's a process called spanning tree algorithm. Spanning tree algorithm, STP. And the spanning tree algorithm takes all the interconnections that are in the network created by how people wired them together, eliminates loops, and makes it possible for only one path between every source and every destination. So here our little tree starts with the root here, and this is one path and the route to the second path. And if we have a packet that's going to go from this computer to this server, it's going to follow one of those paths like this. And if we have another packet that's to go to this server, it'll follow a different path because the tables in the switches tell it which ports to go out. Now I'll give you just a minute or two to answer this question, to think about this, but if you understand the process here, even though we have these extra cables here, they've been disabled by spanning tree. I want you to try to imagine what happens if all of a sudden some jerk gets into the telco closet and disconnects this cable. Spanning tree is going to fix that probably within a second or so. Spanning tree will fix it if this is disabled, and it'll turn the link on in order to recreate the tree. Which link would get turned on? If this one gets disabled, which one gets turned on? The most likely answer is this one here, because then we'd have a path this way and a path this way. I actually have a friend that went into one of my clients and saw that there were loops in their switch network, and he said, oh, that's a problem, and he disconnected cables. You don't need to do that. Spanning tree will take care of that for you. As long as spanning tree is available and turned on, it will create a loopless set of links between every source and every destination. But if we introduce the idea of a VLAN, then things change. VLANs are virtual local area networks. They are apparently separated networks, which really aren't separated. What happens is that by inserting the VLAN tag and configuring these switches, we tell this port here to belong to VLAN number 115. And we tell this port to belong to VLAN 115. So when a packet goes into the switch, which is supposed to go to the green server, it's sent out this port, which is a VLAN 115 port. And it must be routed then across those ports which are connected to 115 until it gets to the destination switch. And at that point it can go out this cable here to get to the server. What that does is make this look like it's completely separate from this network up here. We have one apparent physical network up here and a separate apparent physical network down here. These two networks, even with these cables attached, these two networks cannot communicate to each other if this port's being used, because the packet that goes on this connection here is in VLAN 115. It has to stay in VLAN 115 until it gets released from the VLAN network, which means until it's released out here. The VLANs here are being defined by the ports in the switches. So this port here and this port down here are being assigned to what we're calling VLAN 115. And as a result, packets that are being sent to this server over here will follow the path of the ports that define its VLAN and will not go anywhere else in the network. Likewise, if we assign this port to VLAN 110, and this port to VLAN 110, and this connection over here into the switch, the packet goes in here, the filtering cable says go out this packet here, it gets a VLAN tag for 110 attached to it, stays in here. When it gets here, it says, okay, you can go out of the VLAN now, but you're going to go out of the VLAN to the server. So it controls where the packets go by the VLAN tag. One of the main reasons you use VLANs is to keep broadcasts in this network within this network, and keep broadcasts in this network from getting into this network. It separates broadcast domains. I mentioned earlier IPTV and MPEG transport. In IPTV, broadcast packets that come from servers can be a huge, huge problem. So it's a good idea when you install IPTV to put it on a separate VLAN so that the broadcasts from the data network can't get into the IPTV network. They do the same thing in voice to keep broadcast packets from interfering with voice. So in this case here, I've got a packet that's going to go to the red server, and it's going to follow this path because it's on VLAN 110. I have a green packet. It's going to follow a different path because it's on VLAN 115. A VLAN is not the same thing as a subnet. This is one subnet, but it's two separate VLANs. This is one subnet, but two separate VLANs. I could make it two separate subnets, but there's no need to. Typically, the switch has software in it that allows you to configure it. This is what an inexpensive Netgear switch looks like. You simply go in, say what VLAN you want, check the ports that you want to belong to it. Here's a second one that shows a quite inexpensive little switch. I think these are something like $23 or $27 or something like that. You name the VLAN that you want to pick. In this case, we have VLAN 1, and you decide on which ports go into that VLAN. By the way, by default, VLAN number 1 is always no VLAN at all. In other words, you aren't configuring anything. We'll make this a homework assignment since we're quickly running out of time, but if you understood the concept of subnets, and we asked this question here, this would be a good final exam question for a session like this. If this camera is to be pinged by this device wants to see if it can reach the camera. If you send a ping from this computer here to this camera over here, the question is, how does the packet flow? This way? Does it go up here? How does the packet flow? The slides in the beginning have my email address in. If you want to take a crack at it and tell me how it would flow, go ahead and send me an email and I'll be glad to get back to you and tell you if you're right. So with that, I'm going to turn it back over to Neil. Neil?
Man, talk about taking the lid off of Subnets and VLANs. Thank you, Professor Phil. I've got great news. There's CTS credits for attending this entire series from Professor Phil. Now, the CTS credits are dependent on viewing the entire series. Don't worry. If you've missed one, you can review the recording at starin.biz/AV over IP /. And that is case sensitive. AV over IP is capitalized. We are recording this, by the way, and you'll see a link to the recording, and we'll make sure that you also have the link of where to see previous recordings as well. I wanted to run down real quick before we get to your questions some of the coming workshops that we have. On April 17th, we've got UDP TCP ports and forms of IP video. This session is going to discuss the difference between UDP and TCP, emphasizing the difference in network characteristics that support audio and video streams using those two protocols. We'll also cover port numbers, what they mean, and what their role in configuring a firewall or proxy server are. Finally, we'll take a look at video transport platforms that use RTP, RTSP, adaptive HTTP, and web RTC and how they are related to those previous topics. May 1st is how are keys for encryption created and distributed, and what does it mean to require a device to authenticate to the network. How secure are our AV devices? These are the issues that we're going to cover on May 1st. May 15th, in this session we're going to discuss the MPEG transport mechanism, which is the most widely used format for carrying UP video. While it was popularized for IPTV, sometimes it's even hidden under streaming protocols used by major vendors. Then we're going to dig into multicasting and discuss some practical concerns that seem to come up with the deployments that use the MPEG transport stream. Specifically, we're going to consider some AV products that depend on MPEG transport and multicasting. Now, don't forget our other AV Meetup coffee breaks, which are the 20-minute reviews of Starin products within the IP world. So, Professor, let's get to some of those questions. There was one towards the beginning, so if you'll just bear with me. Here we go. Is 127 for the first byte reserved somehow? And then he qualifies the question by saying, I'm thinking about localhost 127.0.0.1, for instance.
Yes, we actually covered that on a slide back. If you look, 127.0, well, actually 127.anything is typically reserved for my own host. So the commands that would be sent to 127.xxx, anything, is assumed to be sent to yourself. So it's used for purposes of kind of internally testing your own software, internally testing your protocol stack, and so forth.
Thank you. Scott Morgan asks, are the CTS RU credits available for CTSD holders? Yes, they are. Ian, we'll give people time to type in their questions. In the meantime, if I haven't said it, I really appreciate everybody's attendance today. We have a really large crowd, and thank you so much for joining us. Neil Hosier was the winner of the trivia question. Who wrote the song Boogie with Stu? And it's Led Zeppelin. I promise next time we will have a different trivia question. One other question, regarding the four networks we created earlier from 192.168.1.0/26, what determined the 64 addresses in each network?
It's the fact that there are 2 bits being used out of that byte, and the 2 bits allow you to create 4 sets of addresses. You've taken a range from 0 to 255, which is 256 addresses, and split it into 4 parts because you used the first 2 bits. 2 bits allows you to define 4 things, 4 separate networks. So those first 2 bits determine that the range is split up in groups of 64, from 0 to 63, from 64 to 127, from 128 to 191, and then from 192 to 255. Each one of those groups is 64 addresses long.
Gotcha. Thank you. We've gotten this question a couple times. How does 10011 equal 19?
Starting from the right-hand edge, that 1 is worth a value of 1 in decimal or binary. The next one to the left is worth 2. So you have 1 plus 2. The next 0 is worth 4. The next 0 is worth 8. And the left-hand one is worth 16. So you have 16 plus no 8s plus no 4s plus a 2 plus 1. 16 plus 2 plus 1, 19.
Thank you. And then there's a question about what day our AV meetup, the coffee breaks, or the workshops are on. It said you thought they would be on Thursday. Are there Friday sessions? The simple fact is that we typically have them on Friday afternoons, whether it's a workshop or it's the coffee break. This week, with Good Friday being Friday and some businesses working a half day or closing for the entire day, we decided to shift this back a day and make it on Thursday. So typically, all of our AV meetups, coffee breaks, and workshops will be on Fridays. Here's another question. Is dividing the network using masking, which was illustrated earlier, a way to isolate traffic from devices similar to a VLAN?
Yes, it is. In fact, in this case here, we've accomplished essentially the same thing on this slide that we would accomplish with a VLAN. It's just that the router on the left-hand edge is doing the job. So we have a segmented network, 192.168.1.0 on the top, segregated away from 192.168.2.0 on the bottom. In this case, we have 2 subnetworks. And if we did the same thing, took the router out and basically used only switches and created VLANs, we could accomplish exactly the same thing. However, in that case, we'd have a choice of whether we wanted to make it within 1 subnetwork or 2 subnetworks. So routers create subnets. VLANs partition a network. And a VLAN and a subnet can be 2 different things.
You know, Brian has a question that is an offshoot of this one. What is the more efficient way?
That's probably the million-dollar question. In the industry right now, there is a huge controversy taking place as to whether what we would loosely call routing of frames and packets, whether that should be done at layer 2 by Ethernet or done at layer 3 by routers. Avaya, Dell, and HP are behind a technology called fabric technology, that's what they're calling it, which is layer 2 multicasting. And of course Cisco, with their router structure, basically made it popular to do layer 3 multicasting. The routing of packets through layer 3 can also be accomplished through layer 2 with things like VLANs and fabric technology. So there is a gigantic controversy taking place in the industry as to which one is more efficient. The only kind of technical significant fact you can say about the difference between routing and switching is this. When a packet goes through a router, it has to be stopped, read, rewritten, and forwarded. That takes processing time and energy. When a packet goes through a switch, not all of those steps are necessary. The packet does not necessarily have to be rewritten. But in a router, the packet must be stopped, read, and rewritten, and then sent forward. So there is a little bit of an argument for saying it's a good idea to avoid routing when you can. But it's kind of one of those things where, is it going to be the straw that breaks the camel's back? It's not that significant. In most cases, it's a minor question.
Very good. Remember again that we are recording this. And so if there's a concept or a topic like how did we get to 19, you might want to review that. I know that I'm going to have to. That's why I'm glad that this has been recorded. But you might want to review it and go back over it, which leads us to this question from Judith, who says, I feel like I understand what you said about subnets and what you said about VLANs, but I don't understand how they do or don't interact.
Well, I'll tell you one way. If you have to try to create the segmentation with routers, and especially if it's being done with Cisco routers, you're going to have to know how to configure the routers. Setting up VLANs in switches, especially inexpensive switches, is extremely simple. So if you want to segment networks into pieces and avoid the whole concept of the complication of a whole bunch of different commands to try to configure interfaces in a more complicated router, it's much easier to set VLANs up in switches. And so simply from the standpoint of ease of deployment, VLANs are probably simpler. That would be the principal thing I would say about the difference between them. But kind of by definition, a VLAN is a group of devices which are reading that tag in the Ethernet frame. Subnets, or router subnets, are created by the addressing structure in IP. And so different devices are reading different parts of the data frame in order to determine how to process the frame. Hope that helps.
I think so. This is kind of a two-part question. Are any of these devices ready for IPv6, and how does IPv6 change the game?
I have to admit that I'm not exactly sure. What I can say is that I taught IPv6 in 1997 or 1998 because everybody was saying, oh my gosh, you've got to be ready for IPv6. It's coming, it's coming, it's coming. And here we are close to 20 years later, and what I find really in the corporate marketplace and in AV locations or in AV situations is that 98 or 99% of all networks are using IPv4 and ignoring IPv6. So my frank answer is don't worry about it right now.
Gotcha. What about cut-through switches versus store and forward?
Most switches today are store and forward, and I wasn't sure about that because I had gotten away from switch technology for some time, but right now I'm sitting on a TIA committee with one of the founders of the company that was Anui Systems, which was sold to Ixia, one of the smartest switch guys that I've ever met. And I asked him that question about 6 weeks ago. I said, how many devices are cut-through versus store and forward? And he said, you know, the truth of the matter is that with the speed of the processors in these ASIC chips, it really doesn't make too much difference anymore. So that some switches will be cut through and some switches will be store and forward. But the store and forward action doesn't slow a frame going through a switch down like it does going through a router, because typically unless you're doing something like VLANs or AVB where you're putting in the tag, there isn't a rewriting operation taking place. What slows packets going through routers is the fact that as it goes through the routers, the hop count gets changed, and because the hop count gets changed, you have to recalculate the checksum, and that delays the packet. That doesn't happen with the switch.
One other question, does 01010 equal 10? And if there is an additional digit to the left, does it represent 32?
Well, the answer is yes, it does represent 10 because it is 8 plus 2. And if you put a 1 on the left end of that and make it 10101, then it would be 10 plus 32, 42.
Gotcha. He says thanks.
Okay.
Next question is, I've worked in some environments where there are multiple VLANs, but you could still communicate across VLANs. Is that something you can go into? Is that done in the routing?
Yes, exactly. In the slide that's up now, if this would be a VLAN up here and this would be a VLAN down here and I wanted to connect them together, I'd simply attach a router and it would go between the two VLANs through the router. The router would think it had this physical network up here and this physical network down here. The way it's wired here, it doesn't make any difference, but even if we had a whole bunch of other wires interconnecting these devices and we had this defined as one VLAN and this defined as a second VLAN, they couldn't communicate unless they went through a router. You've got to go up to layer 3, up to the routing layer, to interconnect VLANs.
I believe we've come to the end of our questions.
Okay.
Thank you, Professor Phil. Terrific session. Thanks to everybody that's joined us, and thanks for spending time with us at this AV Meetup workshop. And we'll keep you posted of other AV Meetup workshops and coffee breaks, and we'll send you, of course, the link to where you can view the recording of this and review it as necessary, and pass on to your colleagues that may not have been able to join us. Thanks again, everybody. Have a wonderful day.